morning, my name is Guido Parissenti, and today I'm presenting an example of a real space mission that we are developing here at GP Advanced Projects, the FEAS program. My presentation will go through an introduction about why we go in space, an history of the early day of space science, and an introduction about the new space. We'll talk later on about the space environment, satellites in general, like CubeSat in particular, and the activities at GP Advanced Projects, like the FEAS program. So, why do we go in space? There are many purposes. First, in history were the military purposes, with communication services to be safe from ground activities, the control and survey from space of the activity of the enemies, and the defense of the space assets themselves. Luckily, there are more peaceful purposes like the science motivation with the observation of Earth from space, but also of the observation of the universe, because from space we can see much more frequency that are not shown by the Earth atmosphere. And also new activities in biology in space. Obviously, there are also business purposes. First in history were the television, broadcasting, communication. Nowadays, weather forecast and space tourism are skyrocketing. When everything started, in 1985, a Russian math teacher, Konstantin Tsiolkovsky, developed the first rocket equation, which describes the physical principle of rocket development. In the 20s of the 20th century, there were already an active group of researchers in Germany. Hobart, in the 1923, discussed first in history about a space mission, space flight and space telescope. His ideas were discarded by the community because were considered too advanced for the time. But Hobart's ideas were considered fascinating by Wernher von Braun, which eventually became the designer of the Nazi V-2 during the World War II, and later on in US developed the Saturn V, which brought the man on the moon with the Apollo mission in the 60s. Just after the war, at the end of the 40s, the V-2 code to Nazi were used for the first scientific mission for ballistic flights up to 160 km for scientific observation. At the end of the 60s, the USA Army proposed to place a satellite in orbit, but the proposal was discarded in favor of a USA Navy project. But meanwhile, the URSS placed 3 always more complicated satellites in orbit, the Sputnik 1, the Sputnik 2 and 3. To catch up, USA placed in 1958 a very small satellite in orbit compared to the Sputnik 1. But they were lucky because they discovered a very scientific phenomenon, which is the Van Allen belt that protects the Earth from the cosmic radiation. After the Explorer 1, many other satellites were sent to space for science and enabled the birth of the IR, UV, X and gamma ray astronomy and planetary exploration and study of the extrasolar planet. So, thanks to space, we can look to the sky with different eyes. Nowadays, we are observing the newborn new space. The new space is a movement and a philosophy which is encompassing a globally emerging private spaceflight industry. New aerospace companies and ventures are working independently of government and traditional major contractors to develop faster, better and cheaper access to space and spaceflight technology driven by commercial, as distinct from political or motivation to broader, more socio-economic oriented ends. The new space is targeting many kind of mission, from suborbital flight with tourism, research or point-to-point travel, orbital flight for space tourism, research and point-to-point travel, but also deep space flights for tourism, explorers, research and mining, and in-situ resource utilization to service a space-based economy. So, thanks to the new space, we are trying to change the world. As you see, SpaceX is one of the companies which is more actively working in the field. But going to space is not an easy task. Space is a highly dangerous environment. A space system which is going to space has to face many problems coming from vacuum, which is removing volatile from the surface, cold welding, difficult in its transfer. The atmosphere is still present up to 600, 700 and even 1000 kilometers and is provoking drugs, and the atomic oxygen is basically heating your satellite. There are micrometeoroids and space junk which is traveling at many tens of kilometers per second, destroying your satellite. There are high temperatures and very low temperatures, and this cycling from minus 120 to plus 120 is very dangerous. It's not careful design. There are radiation, non-ionizing radiation that are provoking heating and degradation, and the solar pressure that is moving your satellite from the orbit that you selected. But also there are ionizing radiation, which are provoking charging, sputtering, and single event effects, which are basically destroying your electronics. So a satellite, in order to survive in this very difficult environment, is composed by many subsystems. The satellite is basically divided by a service module and a payload. The payload is the motivation for why you go in space. Can be a telescope, can be a transponder for communication, can be whatever you want. And the service module is the part of the satellite that allows the payload to survive and to perform its mission. The service module is composed by a structure that allows the satellite to survive the launch, a thermal control that allows the satellite to remain stable in the cycling environment of the space, a subsystem for power generation and distribution that provides the requested power, a data handling subsystem, the computer that manages the generated data, a communication subsystem which allowed to receive command and transmit data from and to ground, an attitude and orbital control system to allow the satellite to be oriented in the required direction, and a propulsion subsystem which allows the satellite to remain in the selected orbit. Obviously, not all the satellite contains all the subsystems. The smaller satellites, for example, usually do not have a propulsion subsystem. But nevertheless, this is a very general classification that is applicable to all the satellites. So, a particular class of satellites are the CubeSat. The CubeSat is a standard developed in 1998 by Cal Poly and Stanford University, which became a standard for many projects. The specification defines a 1U CubeSat like a satellite with the volume of 1 liter, 10 by 10 by 10 centimeter, and a mass of 1.3 kilograms. There are multiples that can be possible: 1.5, 2, 3, 6, 12U. And nominally, these are classified as nanosatellites because they are in the range of 1 to 10 kilograms. But if you go below the 1U, you became a picosat because you enter in the class from 0.1 to 1 kilograms. The CubeSat were born for educational purposes in university to allow the students to test their skills on a real satellite. But and nowadays they are supported by a national space agency like the NASA CubeSat initiative, with the deployment from the ESS, the Vega European launcher, and other initiatives. The launch cost is relatively small, from 1 to 100 kilo euros, but you can fund for academics sometimes launch initiatives for free. A specific deployer, as in the previous image, was developed, the P-pod, which allowed each CubeSat to be launched by a variety launchers. These characteristics of being in a standard which can be launched at low cost from many launchers, and the fact that in the years the electronics decrease in dimension and allowed to place more and more functionalities in a volume which previously was big, attracted the interest of also commercial companies. So nowadays the CubeSat are used not only for educational purposes but also for business purposes. For example, here you see the 3U CubeSat of Planet Labs. Planet Lab placed a constellation of 150 CubeSat, of which they will to go through 300, which are able to take a picture of the whole Earth every day with a resolution on ground of 4 meters per pixel. So what we are developing here at GV Advantage Projects. Let me introduce who we are. We are a small enterprise. We are born in 2015 and we are located in Italy. And we are helping companies in entering the space field, but at the same time we are developing our products. It's projects about space-related components, specifically in the field of CubeSats. We have various collaboration with many research institutes and other companies all around Europe, and also to space agency like the European Space Agency and the Italian Space Agency. We are also involved in many programs regarding high-energy astrophysics. For example, the XP and Theseus projects are related to the development of astrophysics telescopes from space to study X-ray polarimetry and the gamma-ray burst. Since 2016 we started the developing of FEES, which stands for Flexible Experimental Embedded Satellite. The FEES is a 0.3U CubeSat and it weighs only 300 grams. Nevertheless, despite its very small dimension, it contains the majority of the subsystem that you can find in a bigger satellite. We have obviously the onboard data handling, we have the telemetry with the possibility to send information and data to ground. We are stabilized on 3 axes thanks to many sensors that allow to determine our attitude, and magnetotorquers integrating into the PCB that allows to control the orientation of the satellite. And we have also some experiments on board. We are a radiation experiment, the RADEX. We have a Raspberry P0 with an SDR and camera which allow to take picture of the Earth. But also we are testing some experimental solar cells and a new way of communicating thanks to an iridium transponder. We will be launched at the end of this year from a Soyuz launch in a sun-synchronous orbit. At the moment, we have performed our qualification campaign in June of the last year, and we are finishing the manufacturing of the flight mode. The history of FEES development was quite long because we suffered 3 change of launcher. At the very beginning, we were supposed to be launched by the Dnepr Russian launcher. After that, we got the launcher changed, and we were supposed to be launched with the Falcon 9 of SpaceX. And later on, again, our launch provider changed its launcher, and now we are aimed to be launched with the Soyuz. So our developing started in 2016, and we made basically 3-year development with the prototype and manufacturing and testing. In July of this year, we will finish to assemble the complete flight model that we'll deliver in September of this year for the launch expected in October and November. So what you see in this slide is the qualification model of the FEES. As you see, it has been tested in vibration and thermal vacuum in the June of the last year, and as I told you before, we are going in these days for the manufacturing of the flight model, which will be subject to acceptance testing before being delivered to the launcher, and we are finishing writing the firmware of the satellite itself. This slide is quite messy, but I want to demonstrate that each satellite basically contains all the same subsystem. As you can see, despite the FEES is very small with a mass only of 0.3 kilograms, it basically contains the same functional subsystem of a much bigger satellite, like the Sentinel-3A of ESA, which weighs 1250 kilograms. So we are both having the power generation and distribution subsystem with the solar panel and battery. We have data handling unit with our microcontroller unit that do the same job of the PCDU of the Sentinel. We have a thermal control with radiating surfaces on the exterior of the satellite. We have our communication parts like the antenna and the transponders, and also we have the attitude and orbital control system. Sentinel is using different means respect to FEES, but the purpose is absolutely the same. And obviously we have a structure that holds the satellite to the launch during the launch. We are only lacking the propulsion subsystem that would have been very difficult to place in such a small object. FEES is very suited for educational opportunities and purposes. We are thinking to extend this demonstration product to a real product for university that can develop their own space program at a very much cheap cost with respect other solutions that are already on the market, with the goal of democratizing the space. Our platform allows also to have a bigger payload respect to the 0.3U that you see before, because we can keep all the electronic in the same volume, but we can extend the structure reaching back the 1U or 2U size, allowing to have much more payload on board. Thank you very much, and if you have any additional question, you can contact me or Hanna Molmital, which helped me to build this nice presentation, for any question. Thank you.